So hello everyone. This will be my persuasive speech. This is a presentation I had to give at work on a process improvement that we did recently. This just shows the benefits that the improvement made compared to the old process. So I'll walk you through. This is the assembly that we made the process improvement on. What we do is we make end plates for air springs. What you see here is the end plate with the two components. These will be the main focus of what we made our improvement on. So from the old improvement, or from the old style of how we used to assemble these parts, we would put those two components in one at a time. What we're doing now is we made an assembly fixture that would press both of those components in simultaneously, one stroke. So essentially eliminating your cycle time by just about half. So we'll walk you through, kind of show you what kind of improvements we made. This shows the initial time trial that we did on the old style of assembling that part. We broke it down into each station. So you have 3 steps that go into assembling that part, and each step is done by a station or a person, an operator. So our first assembly, what we call, they would be putting in one component. It will take them about 6.1 seconds to put that one component in. That's from the time that they would pick the plate up till the time that they set it down after completely assembling that one component that they're responsible for. The second assembly would put in both of those studs. That was one of the that's the area of focus that we did for our process improvement. So putting in one stud at a time, it was taking them 8.1 seconds, which was 0.4 of a second slower than our first assembly. So that was where we identified our bottleneck. And so that second assembler, being half a second slower than the first assembler, they were constantly getting backed up, and to the point where their parts would back up into the first assembler's area, causing them to have to stop, let the second assembler catch up, forcing them to stop, let the second assembler catch up, which was just slowing them down, and then it would eventually back on up into the press, just slowing the whole line down. The ringer, which is the final stage in our assembly process, was running at 7.7 seconds, which is nearly 2 seconds slower than the first assembly. So both of these here were causing a bottleneck that would backflow the entire line, causing the entire line to get backed up, slowing the whole process down. Our second time study, this was when we initiated the assembly fixture that would assemble both studs simultaneously at the second assembly press. When we, just by using that assembly fixture, we shaved off nearly 3/4 of a second. Now we're down underneath the cycle time of the press up there. So where we were running at 8.1 seconds, we were 0.4 of a second slower than the press. Now we're underneath that press's cycle time. So we made some progress. We're looking better. Definitely have a better flow to the assembly line. Or by doing that, we were able to free up the second assembly some to help out the ringer, the third station in our assembly process. By doing that, we shaved off a second and a half off of the ringer cycle time. So we made some good progress on that second time study just by putting in the assembly fixture that would drive in both studs simultaneously. The third time study, this was so this one we're still using the assembly fixture. We have we installed a flat backstop to help the assembler align the part and correlate the part to the assembly block. By doing that, we gained another half a second off our previous time. So now we've gained a little over a second, probably looking at a second and a quarter gain by these two improvements. We also moved the studs, the application that we were doing at the second assembly, we moved it up to the first assembly just to shift our bottleneck forward, hoping to open up the flow of the line. By doing that, we were able to, the second assembly will be able to help out the ringing, the third station in our process. So now you have your press cycling at 7.7 seconds, your first assembly cycling at 7 seconds, your second assembly at 4.5 seconds, your ringer is slightly under 7 seconds. So now we're underneath the press's cycle time, so we were able to get a decent flow to the line. It's still not where we need to be, but we're making progress. So the final time study, this is where we switched to a longer diameter ring for the ringer station. We wanted to try to improve our assembly time at the third station, the ringing station in our process. So the previous ring that we had was, the inner diameter was a little tight for the fit, which would make the application a little tougher. So we went to a larger diameter ring, made the application a lot easier. This showed in their cycle times, which we were down from nearly 7 seconds to slightly under 3 seconds now. By adding the flat backstop and switching to the larger diameter rings, now we gained nearly 2 seconds on our stud application from our previous time trial. Our air fitting application is at 4 3/4 seconds. The ringer's application is slightly under 3 seconds now. So now you have a good healthy flow down the line. Each station, starting from the press, each station down is slightly quicker than the last one. So you have a good healthy flow. This shows our initial trial, which was the old process of how we assembled that assembly, versus the final trial, the improved process using the assembly fixture that we installed that would put in both studs simultaneously. So with initially our old process, we were putting in an air fitting on the first assembly, our stud application on the second assembly, our ringer, which was applying the rings. Now, to the new process, the improvement that we made, the improvement to the process that we made, we switched out the location of the applications for the studs and the air fitting. So now where you had the air fitting at the first assembly, we repositioned that to the second assembly, the stud application went from the second assembly to the first assembly, along with, like I said, adding the assembly fixture that would drive both studs in simultaneously, the backstop to help correlate the plate, line it up for the assembler operator, and the larger diameter ring. As you can see, we gained from our air fitting application, from moving it to first assembly to second assembly, we gained a little over a second and a half. From the stud application, moving it from second assembly to first assembly, adding the fixture, the backstop, we gained shade over 3 seconds. The ringer, by going to the larger diameter ring, along with the rebalancing of the line, the second assembly being able to help them out some now, they were down from 7.7 seconds to under 3 seconds now. So now you have the most optimal flow that we could get, whereas versus your bottleneck being here, slower than your press's cycle time, which is feeding the line. Now each station is quicker than the press. Along with each station, as you progress down the line, each station being slightly faster than the previous. This shows what our cost savings would be by going to this improved process. So in 2018, we were averaging over a 12-hour shift, 3,416 pieces assembled. The last two trials that we seen in the previous slides, we assembled 4,300 pieces and nearly 4,500 pieces, a gain of over 900 parts per shift. How that equates into dollars, at $250 per hour average total overhead that we have on that assembly line. The previous process at 3,416 pieces average in 2018, we were building each part at 87 cents per piece. The improved process at 4,300 pieces, we are down to under 70 cents, 69 cents per part. So now you have a savings of nearly 18 cents per part. And this is a high volume part that we produce at our facility. At 18 cents per part savings across 330,000 units per year annually, we would save approximately $60,000, nearly $60,000. So we seen that this was probably one of our most difficult assemblies that we do at our facility. So we thought we had an opportunity to give better flow and improve on that assembly. I think we succeeded at that. So this was my persuasive speech. Thank you all for your time. Any feedback would be appreciated. Thank you.